Okay, continuing on the beam top nailer. This for the because we have the links on either side, so in between you cannot get the nailer in there.
The thick zone.
Yeah, this is the kind of protective zone, right? So this dimension is typically 17 and 7/8 inch. 17 and 7/8 inch. Okay, so here's the beam length that we have. You subtract these two out, okay, then you get the nailer length, approximate nailer length. Okay, I didn't put in the gap, so 64.25. So after you figure out what that is, now how many bolts do you need to transfer the load to the beam top flange? And the bolts are 3/4 inch diameter, 8307 bolts. Okay, so that's what they are. Luckily, this is really set up in an Excel spreadsheet, so we know the capacity of what a 3/4 inch bolt, 4x single 4x. We actually account for the countersink, and then the bolt geometry and allowable loads. So for our bolt, we get the increase. So you get about 3,200 pounds per bolt. So all you have to do is come in here, input the lateral load, okay, of let's say how many kips. We multiply by the omega value. So the bolt design, we have to do omega value because we wanted to transfer the shear into the frame. And now number of bolts required is basically that number divided by that. You get 13.87. Let's say use 14 bolts. Okay, the bolts have to be a even number because we always do it in pairs. Okay, so that's if it says 12.7, you cannot just say 13. You have to go to 14. Okay, now your beam length is 100 inches. The nailer length is 64.25. The bolt spacing is 8.04 inches. We say this, okay. So you'll see where these comes from. Okay, so we want 14 bolts. The nailer length is 64.25. So you go with 64.25 minus 2 times 8. There's the 8-inch here, two sides. That's to the first hole, divided by the 14 divided by 2. Basically, here's this how many spaces you're dividing. So it's 1, 2, 3, 4, 5, 6, 7. You could do right. 7 divided by 7 subtract 1 is 6. So that's 6 spaces we have. Okay, and when you lay it out, going from the 2.5 and 2.5 is to cover the link sticking out at the end here. That's 1.75. I mean, we get it, and plus another inch is 1.5 plus another inch. The gap between the nailer and this one, you get the 2.5 inches. Okay, so 2.5 inches, and we get this as the end distance, this as the end distance, and in between, we're getting about 8 inches. So that's what that nailer looks like. For 3/4 inch holes, again, the holes has to be 1/16 oversized, so that becomes 16 inch diameter holes. These holes are from a connection. These holes are from connection. These are for the nailer, top nailer connection. Okay, so that's pretty much it for the nailer design. You just go in, plug in your lateral load into the frame, divided by it. If you have multiple bays, then this one I said 2 beams. Assume half of it is going into each beam. So we have 2 beams that dragging on a load. I say for each connection, that's how much we think that's going in. Okay, so we have 3 beams just to see how the load is distributed in there. So what if S is smaller than 6? We place a limit on this. So we don't want to punch too many holes too close to the flange, right? So we set, let's say, 6 as a minimum distance. So one is option is verify if omega 2.5 is okay with for flexible diaphragms, or default is omega of 3. So if your omega of 2.5 is okay, then this will have smaller forces and less number of bolts and greater spacing. So the first check. Option 2 is see if they could drag the low into the frame from the column or from any other other solution. So like I say, this one we allow them to weld the bracket and drag it in this way. This one this is from wood, so I assume that the low is not too much. But when you have a low applying, you should also be checking on the local buckling and all the strength of the stiffener as well. So this one I show it as something that goes all the way across. Okay, so this is actually, you need to check the flange if they're going to be dragging low into that side. So on that one, all you have to do is you could actually use the same Excel sheet and just modify it. Instead of doing the PR length, then you could just apply the low, how much is dragging in, and I would look at it as omega phi low as well. Okay, so 15 kips, we'll do it times 3, 45 kips. This is typically usually a lot less than what you have from the link, but I can't be sure. If somebody's trying to drag all the load within this one, then yeah, you need to check the column for that and see if stiffener is required. If it is required, then you just do one that's all the way across. Right. So that's the second way of doing it, dragging it through the column. That's pretty much for the nailers, for the beam top nailers.
The bow, not the nail.
The nails are typically the engineer record.
Yeah.
Right. We sell them the frame.
Yeah.
They make sure they could transfer the load into the frame. Yeah. We on the catalog actually publish the number of nails as well, and SDS screws. Yeah. So if you want to do that in that case, that we could help them out. How many SDS screws we could. Basically, you take the same number, the 47 skips or whatever, and then divide it by the screw or the nail capacity. Then they know what number of nails. Yeah. So yeah, good question. The nailers on the column and then the bottom of the beam, we do have some capacity assigned to them as well. And this was calculated by, I think, either Sam or Brian in branch 23. They're out playing for wind loading. Let's say if they have a window, they want to make sure that the pressure is okay, they can support it. So those are pre-calculated. So I could just give it to you guys the PDF. You could just include in the cal package if they ask you what it is. So that's what it is. Review. So design 4x beam top nailers to transfer lateral load into the frame top, the beam top. Alternatively, the lateral loads could be dragged into the column with a shear tab outside the column. All you have to do is use this Excel spreadsheet to calculate the number of bolts and check the minimum bolt spacing, and then try to maintain a minimum bolt spacing of 6 inches.
Do you have any comment for the hold down? Connection hold down on the beam.
We have not generated anything yet, but let me show you what we have as a some installation sheets for the OMF. But I applied that to the SMF as well.